So whatever it is I'm going to tell you is joint with, this is, do you have, yeah, you do. With Bobby DeMarco, who's a graduate. Tell me if I'm writing too small. Is okay? Okay, so who's a graduate student at Rutgers. He's a Homeland Security Fellow. So nothing I say can leave this room. All right, what am I going to talk about? I've unfortunately used up almost all my energy getting here. And so I don't know what's going to happen. We're going to talk about this. This is the random graph, GNP. I can't imagine I have to fill you in on it, really. But I have n vertices, and I flip coins for the edges. Every edge appears with probability p, independent of other edges. What do you do with a random graph? You think of your favorite property. Well, a lot of what you do is you think of your favorite property, and you ask when means for what p is the graph likely to have this property? So when is it likely to have a Hamiltonian cycle? When is it likely to be connected? A neater property. In a way, the theme of this, by the way, if there's a lectern here, I guess I should not be writing over there so much. It's okay? I mean, you may not want to see it anyway, so.
There's plenty of people can move if they can't see.
Okay. Where was I? So you, in a way, in the background here is the following kind of idea. Take a theorem that you like for just graphs and ask when is it going to hold. For this thing, a really nice example from the mid-90s is due to these guys. Take Ramsey's theorem. When does Ramsey's theorem hold for a random graph? So when is it going to be true that if I take my random graph, color the edges red and blue, I'm going to have a monochromatic triangle, say. And this was completely settled by these guys mid-90s. Beautiful stuff. So I mean, I suppose you could say, if I ask you, when is your graph going to have a Hamiltonian cycle? This is also, OK, my theorem is that the complete graph has a Hamiltonian cycle, and now I'll see when it holds for the random. This is not so exciting. But figuring out when the random graph has this is nonetheless exciting. All right, at any rate, we're doing this, and here is the one little thing I'm going to tell you about. Let me define T of G. So G is just anything for the moment. But let me tell you, because I'll probably forget to say it, that I'll often do that. I'll just say G when I mean GNP, and then you'll have to figure out when I meant a real graph and when I meant the random graph. OK, so T of G, or if necessary, I might have to say T3 of G. This is simply the largest size of a triangle-free subgraph. So it's the largest size of an H. H should be contained in G, and it should be, that's a triangle. And let me also define B of G to be the, and again, if necessary, B3 of G, to be the, and now I can do this. OK. So you have the trivial fact that T of G is greater than or equal to B of G, and this is, when I say trivial, I mean it. All right. So biproduct graphs are triangle-free, so this is seriously trivial. And you have Mantel's theorem. This is the first case of Theoren's theorem. This is, oh, well, now I have to say 1907. And it simply says that if you're interested in the complete graph, the biggest triangle-free graph on n vertices is the complete bipartite graph. And once I tell you that, you know which complete bipartite graph you should take. You take the balanced one. And so the question we're interested in is, when does the random graph have this? So let's say when does G equal G and P satisfy T of G equals B of G. Let me call that star in case I need it later. And let me, again, I don't really need to say this here, but I should say that this question doesn't actually make sense as written. Yeah, I mean, but I will tend to say this. Does this board move? Oh, yeah. OK, so is that better? All right, so yeah, first of all, when means, well, you know what it means, but it means what P, and satisfy means probably satisfy. And probably, I will tend to say almost surely, except when I need to say something else. Other things people say, somehow this one has evolved a little bit. So it seems to me that people used to say with high probability. And then they started to say almost surely. And then there was the complaint that a probabilist knows what almost surely means, and it doesn't mean this. So now we'll say asymptotically almost surely. But to my mind, you can't possibly mistake almost surely in our context for what a probabilist would expect it to mean. So you may as well help the environment and recycle the thing. So almost surely means with probability tending to 1 as n tends to infinity.
But you insist on equality, though, between...
Yes, yeah, we'll come to, right. So this is, so I want equality. That's correct. I'm a campaigner for equality. I'm also forgetting what I want to tell you. No, I guess I don't want to tell you anything much. So this, the story on this one, we'll come to some other stories in a while, but the story on this one starts with Babai Shimonovich. And this one I'm not sure how you pronounce, Spencer maybe. Spencer, how would you say that? I don't know how to say this. Does that letter appear? What? Spencer. OK, so, but all right, you all know him. In 1990, and they said, so we're trying to figure out what P is that's going to do this. They say it's OK, so star is OK if P is bigger than or equal to a half. Actually, for some constant delta, for some positive delta, they prove this. But I don't think, the truth is I've never seen this paper because somehow you can't get it online, and there's no way I could actually go down to the library and look at it. So I don't precisely know what's in it, but somehow by osmosis I get the impression that this is not the issue. It's just as hard if you just want to prove that. All right. Yeah, all right, but we're not, right. OK, but we're not in that ballpark at all. OK, so they do two things. They do this, and then the second, they do several things, but the other relevant thing they do is they say, what about this? It's fairly clear. If you think about it a little, it's pretty clear that this should hold for much smaller p than a constant p. And so they ask, could you at least prove it with p n to the negative c for some positive constant c? And this was done by these guys, Brightwell and now I'm just going to be silent for a moment. And Angelika Steger, a few years ago, '07, I think. And all right, so they do prove this one with C something like 1 over 250. You suspect that, if they had to do 1 over 249, they probably could have. And they ask, or kind of, they say, well, as far as we know, it could be true here. All right, and we will do that, but maybe it's worth saying for a moment, so question. Why is that what I should be looking at? And the answer is, more or less, the answer is, you do want your edges to be in triangles. Okay, so what am I after here? I'm asking that the biggest triangle-free subgraph of G simply be the maximum cut. Be the biggest bipartite graph, be the maximum cut. Now, if you have a number of edges floating around that aren't in any edge, here's an edge. It's not in any triangles. If it's not in any triangles, then it has to be in every maximum triangle-free subgraph. If you have a lot of these things, there's just, heuristically, there's no reason to think there's going to be a maximum cut that contains them all. So, all right, so at a moral level, the statement should be true. If you want it at a practical level, you can say, for example, formally, so this is these guys. If P is less than, and I'll say in a minute what less than is, then there exists, say, for example, a pentagon of, and why don't I make up the name and say of edges that aren't in triangles? All right, so if P is a little smaller than what we're going to talk about in a minute, then you'll find somewhere a pentagon of edges that have to be in every triangle-free, maximum triangle-free graph, and therefore property star is not going to hold. All right, so at any rate, the theorem is, well, OK, so maybe I should say, when do you have this property? So call this property this, right? So you have this when P is bigger than constant n to the minus a half, square root of log n. Now, we could be precise here, but it won't really help us very much. What are we talking about? If you have a pair of vertices x and y, then the expected common degree, the expected number of common neighbors, is n times p squared. If you want to say n minus 2, you may, but I'm not going to. All right, so it's n times p squared. So this tends to be large if p is bigger than, somewhat bigger than n to the minus a half. So when this happens, you start to find that most edges are in triangles. Most pairs of vertices have common neighbors. Most edges are in triangles. But as you know, or probably know, I need to get this expectation up to around log n. If I don't want to see any edges, any pairs of vertices with no common neighbors, then I need the expected value to be log n. That means the probability of failure is like 1 over n. OK.
So this means that every edge lies in the triangle.
Well, I was vague, but apparently that's what it means, yeah. Yeah, yeah. So if I want every edge to be in a triangle, then the truth is C should be like 3/2, I guess. But never mind, okay, because whatever I'm about to talk about, we have no chance of getting the right C anyway. All right. Okay, so at any rate, the theorem is, and it was already, you already know it. It was in the abstract, and
Assume that C squared has to be 3/2.
oh, C squared, yeah, square root of 3/2, yes.
Can you ever graph for every edges on the triangle, but TG is not equal to DG?
Yes, I think I could do that. Yeah, certainly. I'm trying to, yeah, because you could, yeah, I mean, so let me digress. I'm sorry, say again?
Take an arbitrary graph and add a node connected to everything?
For example, yeah. Let me give. I mean, the answer is this is yeah. There are lots of answers to this, but in a way, here's a nice one. Which gives me a chance to mention things that I like that I'm not going to talk about anyway. If I want to come back to this, so this was a problem that went back to the original Erdős-Rényi 1960 paper on that started this whole study of random graphs. Was answered eventually by Komolcs and Szemerédi, Bolobash, Posho is another, a lot of names that seem to share a nationality. The nice version of this, the nicest version of this is this. You take your empty graph and start throwing in edges. And you stop at the moment when every vertex has degree at least 2. Right? You must have degree at least 2 for a Hamiltonian cycle. And almost certainly at that moment, you will have a Hamiltonian cycle. So somehow, in a very literal sense, vertices of degree 0, or let's say vertices of degree 1 or less, are the obstruction to having a Hamiltonian cycle. And so you could ask, I could come to your question and say, OK, what if I keep throwing in edges until the moment when every edge is in a triangle? Am I going to have property star? And the answer is no, unfortunately. Because you could be in a situation, again, what star says is the biggest triangle-free subgraph is the maximum cut. Well, maybe here was sort of an edge which wasn't in any. This is the last survivor, the last edge that wasn't in any triangle. This was the maximum cut at that time. And now I add the edge that puts this in a triangle, but maybe the edge I added was this one. So maybe that edge was already there, and I added this edge. Now this guy is in a triangle. But this is still the maximum cut. And so now this cut plus that edge is a triangle-free graph that's not is a bigger triangle-free graph than the maximum cut. Am I making sense? OK, so it's a little funny. And another thing I should say later, but I'll say it now as well, this is not an increasing property. If I give you a graph with property star and I add some edges, it may not have property star. So it's yeah, you're stepping on my lines, but yes, but you always do. Yeah, so let me come back to that. Just don't listen to him. Listen to me. All right, so you have to tap this thing every once in a while or it falls asleep. Edges should be in triangle theorem. I still didn't tell you the theorem, so here's the theorem. So this is with Bobby, whose name is here. And it says there's a C, and again, I'm not going to be able to tell you the C, such that if P is bigger than C, n to the minus a half, that's a 1/2, square root of log n, then almost surely you have that the largest triangle-free graph, subgraph, is the largest biprotect graph. OK, so now let me come back to the remark that I wouldn't let Noga make. This is, I don't know if this is wise, but so I will probably make a number of remarks at this point. The first remark is this is not a threshold, right? So if I'm interested, thresholds look like this, right? Here's P. It goes from 0 to 1. here is the probability of, let's say, Q. So Q is a property. You know, and again, I seem to like the property Hamiltonian. I like the property connected. And there are some other properties we like. But you tend to think that the graph does something like that. All right? At the very least, it's an easy, soft argument that if the property is increasing, meaning that throwing in edges does not destroy it, then this is an increasing function. Right? But if you are thinking about the property star, then one thing you know, so the same framework as over there, is that this is a point on the graph, and that's a point on the graph. Right? When you have no edges, the graph is bipartite. So yes, the biggest. And even for a little while, if p is small, you don't have cycles. So initially, the graph stays bipartite, and star is kind of trivially true. And so unless you think that that's actually a straight horizontal line, this doesn't seem to be an increasing property. Here's a ridiculous question, and honestly, I didn't think about this. Could it do something like this? So is it true that this thing is, I don't know if I'm allowed to say unimodal for something that goes down and up rather than up and down, but anyway, is it possible that there's only one local minimum? I don't know how you would prove that, but it doesn't seem unreasonable.
When you'd expect it, wouldn't you?
I think so, but I'm a little hesitant. I don't know. Because
How close does it get to 0?
this close. It gets close. Sure, because in intermediate, you start, when the graph is pretty sparse, but you're starting to see isolated cycles, pretty soon you're going to see an odd cycle, and then you're dead. So yeah, it does get close. Okay, let me, I think I want to start wandering a little. So we had kind of alluded to some of the related questions one could ask here. Let's see. So, well, the first one is actually something that will have probably occurred to everybody already. Why is he talking about triangles? Why don't you define TR of G to be the maximum size of an H? By the way, I never did say it, but everybody seems to realize that this is the number of edges. So I want H to be contained in G. And now I want it to be KR free. And if I'm going to play that game, then of course I want to change bipartite to whatever prevents a KR. So this would be maximum H such that H is contained in G, and it's R minus 1 partite. And you have really the obvious conjecture. So the conjecture, and I don't even know if there's an attribution. I've never seen it in writing, but it's the obvious conjecture. If I want to know when does this happen, and again, I'm not thinking about the bottom, which is kind of boring. I'm thinking about the top. If P is bigger than C sub R times n to the minus 2 over R plus 1 log to the 1 over R plus 1n, then almost surely TR of G is equal to BR of G. And as threatened earlier, G is GNP. If you don't really deal with this stuff, you may find these horrible expressions horrible. And they are, but what can you do? That's the answer. And all it means is this is where every edge is in a KR. All right, so that should be true. The reason I only talk about, well, you can probably guess the reason I only talk about triangles. Yeah, we thought that this would quickly lead to this. That so far is not happening, but all of this stuff is pretty recent. So I don't want to completely give up on it. Let's see, what else? Oh, yes, thank you. Yeah, so have I erased them already? No, they're down here. Yeah, Brightwell et al. So Brightwell, P, and Steger prove that it's OK if P is bigger than n to the minus CR. So CR is some positive constant. Presumably, it's small because it's 0.004 when R is 3. But at any rate, so you do have something like that. So their proof just extends directly. Our proof doesn't extend at all so far. Another in this list of tangents. So here's, now I always seem to wind up talking about things I would never talk about. If I give you a graph F and a graph G, but you should think of F as fixed and G as big, then this is, I think we say, Turon density. But I guess I have to say a Turon density of F in G or G in F, I don't know. But at any rate, all this is well, I want to say it's the largest size of an H. H should be contained in G, and it should be F-free. But that's not what I'm going to say. So that's the number, but now I'm going to call it a density, so I want to normalize it. So I'll do this. All right? And in particular, the only one we'll actually look at is this one. And this is just our old TR of G, again, divided by G. Right? Now, Turon's theorem, which I assume we all know, I'm not about to say it, but it implies, so a sort of small relaxation of Turon says that if you're interested in it, sorry, this is so without the bar means without this, but we won't talk about it. All right, Turon's theorem tells you that so for a fixed R, the density, the Turon density of Kn tends to 1 minus 1 over R minus 1. Because, so Turon's theorem says, if you want to avoid a Kr, the best thing you can do is this, break the vertices evenly into R minus 1, and only, well, forbid edges inside these things, and you can take everything else. And that gives that density. And that brings you to a beautiful theorem. So this is due to David Conlon and Tim Gowers, and independently to Matthias Schacht. All pretty recent. As far as I know, they have not even been published yet. And they say something like this: if you give me an epsilon, then there exists a C such that P bigger than C n to the minus a half, and that's all. Right? Notice we've talked about that. This is where edges are mostly in triangles. Not all, but mostly. All right, and then you probably want a conclusion. It says almost surely the Turon density of G. So now I'll stop writing. This is my GNP. Kr is less than 1 minus 1 over R minus 1. Did I write? Oh, you're right. Thank you. Thank you. Yeah, so, excuse me. So right, I want every edge to be in a KR, I want most edges to be in KRs, and it happens there. And if that's true, then the density is about what it should be in the complete graph. Obviously, if this graph is much sparser, then this is not going to be true. I guess I should say it's easy to see that that's, up to the value of C, this is all you can expect, all right? So call this theorem A, because there's also a theorem B, which is the what people call the stability version. This is, again, Conlon-Gowers, but not Schoch. So the proof, these two proofs seem to be quite different. You notice the seem to be rather than I read them and they are different, but they appear to be different. And in particular, Schoch does not give the stability. So the stability says this. Same P, if P is bigger than C n to the minus 2 divided by R plus 1, then almost surely, what do I want to say? If H is a subgraph, you give me any subgraph, right, which is KR free and which has the right Turon density. Right? If you want, you can stick even a minus epsilon here, but that's not really the point, right? So if you give me any subgraph of H that has roughly the size of the largest R minus 1 partite graph, then, so this is sort of all in here. How can you parse it like that, right? Then H is approximately R minus 1 partite. So I guess in this case, C is C of twiddle.
So that proof is by something like the advanced model.
Oh my God, I lost. Yes, that's right. And they do use, I should say, they use regularity, sparse regularity, and yeah, we'll come to that in a minute. Let me just, I feel like I'm leaving out things that I want to tell you. I don't know. I assume it's obvious that theorem B does imply theorem A. Do I need to say anything about this? I mean, theorem A says they assume the same bound on P, and theorem A says I don't want anything that's much bigger than the biggest R minus 1 partite graph, and theorem B says, in fact, if you're close to that, then you are roughly R minus 1 partite. I haven't defined this, but you can guess what it means. It means I can delete a relatively small fraction of the edges, a tiny fraction of the edges, and make the thing R minus 1 partite. Let me digress further, and well, maybe we leave that.
Imply that the TRG is almost the same as BR.
Say again?
Does this theorem imply that TRG is almost the same as BRG?
Yes. Yeah, because well, let's say BR of G, if I just want to understand the rough behavior of BRG, this is not a big deal. This is, some large deviation, some small large deviation calculation, right? And so this is, and the answer is this 1 minus 1 over R minus 1. And so the real issue is, could TR be much bigger? And this says no. So yeah, it does say that. Let me come back for a minute to.
RG is 1 minus 1 over R minus 1, even much before, even if P is just
You said BRG? Yeah, BRG, that's right. Yeah, no, there's BRG is somehow, it's fair to say BRG is not interesting until you start trying to figure out what it has to do with TRG. Yeah, so the interesting quantity is TRG. BRG is just our ruler, our benchmark. theorem, so I want to talk about theorem A3, or I want to attribute, let's say, theorem A3 and theorem B3, by which theorem A3 means theorem A for R equals 3, theorem B for R equals 3. This is due to, I think I say Franck. It would probably be better not to try, but anyway, it's something like Franck rattle. This is an old result, 86. This one's not so hard. All right. And I will say it's based on a neat little idea of this person. I don't know this person, but maybe somebody here does. But anyway, there's a neat little article by him that has to do with, I think, if I two-color the edges of a graph and look at the number of monochromatic triangles, how small can it be? And other things have happened related to this. Let me not go in that direction. At any rate, theorem A3 due to these guys. Theorem B3 is due to these guys, Kohaya-Kawa. And that reminds me I left something out. Huchak and Redl. And what I did want to say was that this one was a conjecture of those same guys. KLR 97. This paper is this paper. Some of you may have heard there's a famous conjecture called the KLR conjecture, and it is the same KLR and it is the same paper, but it's not that conjecture. But anyway, that was open for 10, 12, whatever it was, years and worked on. There are partial results out there. At any rate, if you're interested in theorem B3, so what does theorem B3 say? It says if P is bigger, here's theorem B3, TB3. I just copy it. If P is bigger than C, n to the minus a half, and H is contained in G and is triangle free, and it contains half the edges, then it's approximately bipartite. So I'm writing it because somehow we thought this is an interesting result, partly because this is not easy. You know, it's not as hard as some of the things on this board, but it's definitely not easy. And it does use sparse regularity, whatever that is. I mean, most of us at least know the regularity lemma, which is really for dense graphs, but there's a sparse regularity lemma. And it follows very much along Semrati's original lines. Another point here is that well, let me say this. We definitely use this. And a question which I have wondered about is, do we really need it? It kind of seems like we shouldn't, but so far we do. OK. That's taking longer than expected. At any rate, first of all, because I thought this is a nice simple statement, just like the question we started with, that should have a simple proof, and partly because I'll say something that will get me in a lot of trouble. I feel like using regularity is cheating. I don't like using regularity. I mean, yeah, all right. Well, I will say something which I wouldn't try to defend, but I will say it anyway. It's like, you know, if you want to prove a theorem using the classification of finite simple groups, you say, OK, we have this class of objects. We want to prove a theorem. Well, what we'll prove is that all those objects look like this. And now we just have to prove it for the objects that look like this. And so I don't know. Anyway, I think if you can avoid using regularity, that's a good thing. So we wondered if you could prove this in a simpler way. And so what we thought was, let us try this. Here's a fact, and this is something you can easily dig out of the Franck-Redl, or Goodman's idea, but out of the Franck-Redl proof of theorem A3. If H, so let me stick to the same P that I was talking about up here, and let me suppose that H is contained in G, and H is triangle free, and h is bigger than, I don't care if it's exactly bigger or not, but something like this, then what that implies, and you can always stick in almost surely if you want, is that we know you're not allowed we know you're not allowed to contain a triangle, but it turns out you also can't afford to have a lot of triangles where you contain one edge. You have to meet most of them in 0 or 2. Okay? And so we thought as practice, it might be interesting to ask this. What if instead of saying most, I say for all? What if you require that you contain an even number of edges from every triangle? And here's a theorem, if we can find a place to put it. So this is, again, DeMarco and me and Aaron Ham, who's another Rutgers student, this one not on the government dole. Let us take p to be bigger than c n to the minus a half square root of log n. So for this result, I'm going to be back in the situation that I really need every edge to be in a triangle, not just most of them. All right? And then we will find that almost surely if h is contained in G, and I'm not even saying anything about its size, but I say that h intersect T is even for all triangles T, then in fact h is a cut. Okay, so an easy way, in any graph, an easy way to meet every triangle an even number of times is to be all the edges going from one side to another in some partition of the vertices. And this is true. This has another name. Just shut up. Yeah. So yeah, another way to say this. So actually, maybe you know something that I'm wondering about. The triangles span. Yes, it's customary to raise your hand. So the triangles span the cycle space. I will say things that have homological meaning. I'm not going to go through the background for this. So there are a couple little embarrassing points to this. The first, so this was supposed to be practice for giving a civilized proof of theorem B3, but what we realized is that you can actually, the first proof of this comes pretty easily from theorem B3. So this is a not very tough consequence. Okay, so you can, if you want, you may say that. This is maybe an exaggeration. If I ask you to do this while I waste the next 10 minutes, you might have trouble, but you do get it fairly easily out of theorem B3. You could sort of say this is oops number 1. Oops number 2 is Roy. So literally a week after we did this, I got mail from Roy Meshulam. Reminding me that we talked about this 3 years ago, or talked about talking about it or something or other. And he sent me mail saying, we were thinking about this, how about it? And I had to say, oops. So at any rate, but you know, this is just the tip of the iceberg. The real question is this. You talk about the clique complex. G is now anything. So as I said, you have to kind of guess whether I mean the random graph or a general graph. This time I mean a general graph. The clique complex is simply, it's the abstract simplicial complex. I will not define that. But it's right, so it has vertices and edges and triangles if they're there, and complete 4 vertex subgraphs if they're there, and so on. And the question is, when do we have, and as usual, we mean this, vanishing k-dimensional homology? And let me not talk about where the coefficients are coming from for the moment, but this theorem that I just wrote is this. The one-dimensional homology of this thing, now this is GNP, but only coefficients in Z2, that does vanish. Whether you could replace this or not, that one I haven't thought about. It could be that that's not hard if you're actually interested in this stuff. So that, I don't think that's a burning issue. But for bigger K, it is a serious question. And again, you know, this is a couple weeks ago. I don't promise that what we did doesn't extend, but it doesn't look easy. What should the conjecture be? I said I wasn't going to tell you. It's the k-dimensional homology. If I say it, so first of all, k means k plus 1 simplices. Right? Sorry, it means things with k plus 1 vertices. So an edge is k equals 1, and so on. It says if you have a collection, let me say it here where it's real easy to say. If you have a collection of k faces, which would be, you know, cliques of size k plus 1, when you add them up, such that every k minus 1 dimensional face is contained in an even number of them, then you can find a collection of k plus 1 dimensional faces whose mod 2 sum. You think of a k plus 2 face as the bunch of k plus 1 faces it contains. I'm screwing up the indices. Think of a k plus 1 face, which is k plus 2 vertices. Think of a k plus 1 face as the set of k faces it contains. So now you can add up a bunch of k plus 1 faces and, you know, look at what they give you in terms of k faces. Yeah.
So when you know, let's say that the triangles don't span the
Yes.
cycle space.
Right.
So there's some extra conditions which would imply then that T of G is not equal to B of G, right? So in the case of like the pentagon,
Right.
where those were sort of free edges that you're allowed, that
Right.
you don't have the triangles spanning.
Certainly not.
And then
I mean, let me slow down. Hold on for a second. You know, if again, if I have an edge that is free, well, you know, assuming that I do find some path that connects its ends, then that's a cycle, and it's clearly not going to be in the triangle space. So almost as soon as you have free edges, this is not going to hold. All right, and then which explains why, again, you need the extra root log. So David, I don't think I answered your question very clearly, but I,
You're going to continue on the homological direction or give us a
What?
hint about the proof?
let me finish up here, and actually, in a way, I can give you a hint about the proof, but it's up to you. But let me finish this story. So let's say the conjecture here, but we can say it sort of like this. I don't know if this is, you say, Roy also wrote to me and said Kala, but he stated a conjecture which wasn't the precise, it was something looser. But anyway, the conjecture should simply be this. If P is bigger than this, then almost surely HK of the clique complex, here you can put your favorite coefficient ring, is 0. Right? Most of the conjectures I tell you, it's not hard to guess what the conjecture should be. It's sometimes hard to prove it. So what should happen here? The same thing that happened here. Here I wanted every edge to be in a triangle. Over there I want every k face to be in a k plus 1 face. And so if you want to know what should happen here, I want some constant times n to the minus 1 over, remembering that a k face is k plus 1 vertices. I'm not done, but I really want every k plus 1 vertices to have a common neighbor. And in order to get the every, I have to give you this. OK. And presumably that's got to be true, but it doesn't look that easy to prove. Very quickly, coming back to the embarrassing points and practice, eventually it turns out that we can prove this, this theorem up in the upper left. So we can do this without theorem B3. Right, number one. And number two, it turned out it was good. It was a good idea to try to practice this way, because we can prove theorem B3 without, not so simply, but more simply. And this would be without any regularity. So to satisfy the one person in the room who cares about this. All right, this last little bit is probably less meaningful unless you're
The Kahn is also without regularity.
No, Schacht is without regularity. Kahn seems to use regularity. In fact, because when you guys posted this talk, the first person I heard from was David Conlon asking, how do you prove this theorem? And I asked, do you know a regularity-free proof of this? And he said no. So I'm willing to trust him. Yes, no good. Keep it short.
So is it true that if you have P is that big, and you have a subgraph in which every degree is at least half the degree in the graph, and it's triangle-free, then it's a cut?
No, I don't think so. I'd have to think about that, but I very much doubt it.
So that's a bit stronger as a thesis.
Yeah, I mean, we don't prove anything remotely like that. I would guess that that's not true.
At
But
some point it would be true, right?
yes, at some point, but
But you think that P should be not treated?
when every vertex has degree more than its degree in the graph, then it will be true. Yes. Let me think about that one offline, but I'd be very surprised. OK, so I don't know. I mean, I can stop. I can give you 5 minutes of hot air.
Why 5? You have to 12 start.
Oh, till 12:30?
Well, because it started late.
Oh, I didn't start that late. Well, you wouldn't let me start. OK, so I'll spend the next 5 minutes trying to figure out how the boards work. I'm not going to try to give you, the proof is not so easy. I would say it's easier than this Brightwell et al., for example, and it's completely different. That proof I did sort of look at. What I'd rather give you is what seems to me the main idea. So what I'll tell you does not literally appear in the proof, but I do think it's the main idea. Maybe one way to formalize this is to say, when we saw how to do this, I was convinced that now the problem is solved, even though it took some time for it actually to get solved. So let me try to show, let me just remind you, we're here. And G is, as you know, GNP. I'd like to show that almost surely you do not have the following situation. A max cut A, B. The notation for max cut may not be very precise, but it will not be hard to figure out what I mean. An XY in A such that this happens. So NB means the neighborhood in B, right? So I am trying to say that you're never going to see this. You're never going to see, or you're almost never going to see this, a max cut AB, X and Y over here, such that all their neighbors are on the, all their common neighbors are on the left-hand side, right? Which looks obvious. I mean, it should be obvious. Notice that this kind of has to be true. If we want the property star, which luckily is still up here, if this fails, now I have to quantify a little bit. If it fails with X, Y, and edge, but that's kind of orthogonal to what we're talking about, so you shouldn't think of that as important. If it fails with X, Y, and edge, then you're dead, because then this max cut right? Then this max cut plus this edge, they have no common neighbors, so you can add that edge to the max cut, and the biggest triangle-free graph is bigger than it. OK, so this has to be true, right? And it should be obvious. Let me tell you something that I don't know, which seems equally obvious. So here's a question. The truth is I don't know what P should be for this one. I suspect what I'm about to say is true for a very wide range of P, even though I can't prove it in the range I'd like. It should be the case that almost surely there does not exist a max cut, say AB, and an X in A, such that the neighborhood of X is contained in B. You'll notice I have this habit of drawing these meaningless pictures, but OK, so I shouldn't see that the situation I described there. That one is, in some sense, a little less intuitive than the one I just wrote down, because if you want a max cut, it is to your advantage. So if you want to put X over here, it's to your advantage to put all its neighbors over here. The problem is that if I declare that, then I lose so much freedom in my choice of, right? This is sort of over here, I'm going to see NP vertices. And now, so I've kind of divided by a factor 2 to the NP the number of possibilities for the max cut. And this should really overpower this kind of minor benefit of making the picture look the way I've drawn it. All right, anyway, I don't know how to do this. So if you want to do something in the next 5 minutes, that would be fine. So I want to show this, right? So let me choose my graph G. But let me choose it a bit at a time. So let me start with the neighborhood of X. And then let me choose the rest. That wasn't so exciting, but all right, let me put off this much. All right, so nabla means this is from Lotzi's book with Mike Plummer, and I don't know how much this got into common usage, but it means the edge is going from Y to whatever I wrote up there. So you choose the neighbors of X, and then you choose all the neighbors of Y except sort of the ones that are going to be relevant here. All right, and then you finish. All right. But let me stop for a moment after the first 2 steps and give that a name. So call that G prime. OK. Is it too? Sorry? Oh, I could still write here. This is what you're. Oh, what, this guy? I guess. Of course, if I want, yeah. Come on. I could use the exercise now. Yeah. So this is sort of the procrastination method, if you will, which is something I am temperamentally well suited for. What do I want to say? Notice 2 little notes. One, all right, I mean, this is not where we use the value of p. The degrees are very concentrated. They're supposed to be square root of n, square root of n log n. They're all very close to that. Second thing, if I give you any max cut, and I give you an x in A, then, or why don't I give you a v, not to prejudice things, then the degree of v in B is greater than or equal to the degree of v in A, because, right, here's v. Again, same fascinating picture. It has some neighbors here. It has some neighbors there. If it has more neighbors here, then I should have put it on the other side. And this might be due to Lotzi. I, for some reason, have this impression that it's due to you. Maybe before you were born, I don't know. At any rate, this is not the deepest of Lotzi's observations. All right, but so this is true. Okay, let us do this. Let ST be a maximum cut of G prime. G prime, this graph up here, before I've chosen this last set of edges from Y, all right? Subject, so it's not quite a maximum cut. It's a maximum cut subject to the following conditions. I want x and y to be an S, and I want the degree in T of x to be greater than or equal to the degree in T of y. And again, notice now, according to what I wrote over here, that implies that the degree, I don't know why I wrote this. Excuse me. So the rule in classes is if I write something incorrect, then I'm supposed to wait 30 seconds for people to regroup. What?
You don't allow us to speak.
I didn't say no. What? You say you would have correct, but you didn't want. Yeah, okay. I suppose I did set myself up for this. Okay, so that implies that the degree of x on the other side, here's, if you like, here's a picture of S, and here's a picture of T, and x and y are over here. And x has a decent number of neighbors over there. All right? So now, let me say, and let me introduce a new notation, which people have used in the past. So with high probability meant almost surely, with very high probability means the chances that it fails are very small. And the reason is that I should have I started up there. So I should have said right, so I'm going to look at a particular x and y and see what's the probability that this goes wrong for that particular x and y, and I have to at least say the probability is less than n to the minus 2. So that's sort of what I would need from the very here, but it'll be much smaller. Okay, so I want to say with very high probability, I have the following situation: the b of g is greater than or equal to the number of edges in this cut plus, so what was G prime? It was everything except the edges that go from y to the neighborhood of x, right? The neighborhood of x in B is over here, NB of x. I'm now about to randomize y. Over here, this is of cardinality essentially NP over 2. Each of these things appears with probability p. I expect that the size of NB of xy is going to be at least about np squared over 2. Notice this is big. This is why I need p to have that extra square root of log n. All right, this expectation is some constant log n, and it will be big. I can promise it will be big, right? And so maybe I should do that, and then I get to write np squared over 2. Okay? And I mean, I have to say the last line or two, but I think most of you can see where this is going, right? I chose S and T to be maximum subject to this. Well, that means that if you give me any AB which sort of behaves like the stuff I was trying to rule out, it's a maximum cut, it contains x and y on the left-hand side in A, and I don't even have to say the last thing. If it's a max cut that contains x and y, then it does satisfy this condition, right? And therefore, it is under the rule of ST, right? This quantity is greater than or equal to this quantity because this was the biggest such quantity among things that satisfied something that this satisfied. So this is true. This is true for all max cuts AB with x and y in A, for all of them. Okay? And so actually what this is saying, I wanted to rule it, we're now done. I wanted to rule out a max cut like this where x and y have no neighbors on the right-hand side. What I've really wound up saying, this is supposed, if you go from the size of the cut AB to the amount of that cut that's here, all you've lost is that thing. And so what it really says is if AB was a max cut with xy on the left-hand side, then the neighborhood in B of xy has to be of size at least about np squared over 2, much bigger than non-empty. Okay, and so once you see that, so that's QED, more or less. Somewhere in here is a QED. Right? And now I will dramatically finish with this board. I mean, the drama being that I'm using this board. Suppose that I have this max cut and I have an F which is a maximum, I might as well call it H, that's what I called it, maximum triangle free. Well, every time you add an edge of H to the left-hand side of the graph, you find that there are lots of triangles like this in G, and therefore there are lots of edges from the cut that you must not use. So every edge that you put in on the left-hand side costs you many edges of the cut, and therefore nothing. So we don't, I mean, so as I said, when we first saw this thing, we said, OK, now it's going to be 5 minutes, and it wasn't, and I don't know how to finish it. And this is not how the proof starts. But somewhere buried in the middle of it, I do think that's the main idea. And I think that's, all right, so now I'm done.
So this observation would be enough if you are sort of close to it. I mean, the trouble is that you have many.
Yes, certainly, sure. If I mean, this does promise me that if I only had a very small number of edges here, that's fine, because every one of them costs me something like log n from the cut. I mean, you have to be a little careful because suppose I gave you a lot of these edges, but they all use this vertex, then I can. It's not quite as good as it seems. I just kill the edges coming out of that vertex and thereby kill all these many triangles. But at any rate, to this day, I don't know how to finish it starting this way. Right.
Then indeed the stability somehow seems to tell you that there aren't so many.
Well, so again, you can't, as far as I know, I can't start it this way. What I should do, I lost the decent piece of chalk. What I should do is start this way and fit a best cut to it. All right, so you start with the best triangle-free graph, which I don't know what it looks like. Here it is. All right, but then I take the maximum cut that contains as much of it as possible, and now I know that not too much lies over here, not too much lies over here. That's by Theorem B3, which, well, at one time was written on the board somewhere, the stability theorem. Okay, but then still, it's somehow, it always seems like you got to do some fiddling. It never just comes out very easily. Okay.
I don't know if it's related. There is a paper of it's related to the thing you said about the parity of cutting the max cut with a triangle.
Yeah.
There's a paper of Hegel where he has this XOR principle where if you take a random 3 CNN, so sort of a bunch of triangles, but literals can be signed, and you have to think about the density, but I think it works up to about n to the 3 halves. If there is a satisfying assignment, it will almost surely satisfy. The closet satisfied will be satisfied in an odd number of places.
Oh, okay.
So it's a very,
Oh, well.
it's-
No, it sounds, yeah, it does sound. I don't know it,
it's
as
a
you can
spectral
tell.
argument, so there's a.
Uh-huh.
But he's not saying all of them.
No, it's not.
Oh, he's not saying
not
the
almost,
majority of,
yeah,
ah,
it's
okay,
not,
okay. Well, then that sounds like, as I said, that sounds like this fact.
Right, yeah. That's
Yeah,
what
but
I-
this is easy. I mean, this is a line or, this is a line or two. This is not hard at all.
There's something different here.
Yeah.
Anyway, yeah, it's just reminded me.
Okay.